SIP9 Hub.
Hello again. Welcome to another episode of SIP9 Hub. And for this video, we will be talking in greater details the Fibonacci sequence and its relationship to the famous golden ratio. But before we continue, do not forget to like this video, hit the subscription and notification bell to stay updated of future videos. We start with a very brief history. The Fibonacci sequence is associated with a mathematician. His name is Leonardo Fibonacci, also known as Leonardo of Pisa or Leonardo Pisano. This sequence was first introduced in his book Liber Abaci in 1202. It all begins with a rabbit story, or actually it's more of a rabbit problem. And in this problem, we have a pair of rabbits, and after a month, this pair of rabbits become mature enough to produce an offspring. So that after another month, that's month 2, the rabbit produces an offspring, another pair of young rabbits. And we see here that after 2 months, the total number of pairs of rabbits is 2. You have 1 pair of young rabbits and the original pair of rabbits, the adult pair. And then after another month, this same rabbit here will produce another offspring. That's their second generation offspring. And then the first generation offspring becomes mature in the 3rd month. So in total, you have 3 pairs of rabbits, 2 adults and 1 pair of young rabbits. So we will simply repeat this process. For example, month 4, the 4th month, that second generation rabbit will be mature enough to produce an offspring. So the original rabbit will again produce an offspring. That's the 3rd generation offspring. The first generation offspring will now give or produce an offspring, and then the second generation offspring here will be, as I said earlier, be matured. So if we look at the total number of rabbits now at month 4, after 4 months, we have 5. 2 young pair and then 3 young pairs. 5th month, we do the same. They will have their offspring, and in total, we have 8 pairs of rabbits. Month 6, we do the same, and here are their offspring. So in total now, at the 6th month, you have 13 pairs of rabbits. 5 are young and 8 pairs are adult. So how is this related to our Fibonacci sequence? Actually, when you look at how the number of pairs progresses after each month, it's really the Fibonacci sequence. These are the Fibonacci sequence: adult pair, young pair, and the total number of pairs. So we now proceed to the definition of the Fibonacci sequence. It is a sequence starting with 1, another 1, and then for each term here is the sum of the 2 preceding terms or the 2 terms before it. For example, 2, this is the sum of 1 and 1. 3 is the sum of 2 and 1. 13 is the sum of 5 and 8. 21 is the sum of 8 and 13. So if we want to know the next term after 21, that should be the sum of 13 and 21, and that is 34. Of course, we can go on as long as we can. It's a never-ending sequence. It's an infinite sequence. To make it more easier, we will introduce a notation here, x sub n. This is the term, a Fibonacci term. And mathematically written, a Fibonacci term is simply the sum of the two preceding terms. So this expression here, x sub n minus 1, is the term before it, just before it, and then the term x sub n minus 2 is the term before or preceding x sub n minus 1. So this means that these are the two terms preceding x sub n. So we simply add those terms. Fibonacci numbers, we are saying it's Fibonacci numbers, not Fibonacci sequence. We mean a specific term in the Fibonacci sequence that is a Fibonacci number. And Fibonacci numbers are really evident in nature, specifically on the number of petals of flowers. We have an observation that most of the petals of the flowers that we have are actually a Fibonacci number. For example, this one here, this a lily, a 2-petal flower, a 3-petal flower, 5, 8, 13, 21, 34. So this sequence is again our Fibonacci sequence. What else? What other things that we can see around us that are Fibonacci numbers? Your body parts. Take a good look at yourself in the mirror. You'll notice that most of your body parts follow the numbers 1, 2, 3, and 5, or the Fibonacci numbers. You have one head, one brain, one mouth, one nose, one heart. You have 2 hands, 2 feet, 2 eyes. You have 3 segments in each limb. You have 5 fingers in one hand or in one feet. Of course, assuming that your hands and feet is complete. You have 8 skull bones. You have 34 bones in the backbone, including the skull. So these are all Fibonacci numbers. In sunflower heads, this is a more visible version of this image here. So we are actually focusing on the spirals, the number of spirals that we have. Let's try to count. We have 1, 2, 3, 4, 5. Let's see where it ends. Okay, we have 12 now, 13, 14, approaching 17, 20, 21, 23, 24. And how many do we have? So for those spirals that are directed like this way, we have 34 counts. How about the opposite spiral? Let's try to count as well. So the green numbers, oh no, I mean the red one. 17, 18, 19, 20, 21. And 21 is again a Fibonacci number. Also in pine cones, if you're going to count the number of spirals as illustrated here, they are a Fibonacci number. So for example, in the left picture, if you're going to count 1, 2, 3, 4, 5 until this one, you have a total of 13 spirals. Also here, if you count these kinds of spirals, this one, you have 1, 2, 3, until you reach the last one, you have 8. And 8 is a Fibonacci number. 3 branches. How does a tree branches out? As a tree grows, let us try to count the number of branches it produces or it splits. Let's start with the first one, and then it becomes 2, it becomes 3, becomes 5, and becomes 8, and then 13. All the numbers here, the number of branches, are again your Fibonacci numbers, and since it's complete, seems that this is already the Fibonacci sequence. Let us proceed to another concept, the concept of the golden ratio. The golden ratio, the symbol is the Greek letter phi, so it's just a number. The golden ratio is just a constant, just like your pi, like your Euler's constant. The golden ratio is also a constant, and the symbol for that number is the Greek letter phi, the symbol that we see here. The golden ratio appears many times in geometry, art, architecture, and other areas. It was first called the divine proportion in the early 1500s in Leonardo da Vinci's work, which was explored by Luca Pacioli, entitled The Divina Proportion in 1509. Now, how can we arrive at the value of the golden ratio? So in this presentation, we will not just be giving the value, but we will also be presenting how we arrived at this constant, at this number. So it actually begins with a simple line segment. For this line segment, we will be dividing it into two, one longer and one shorter. So the longer part is A, that's segment A, and the shorter part is segment B. Of course, if you add the measures of A and B, that is the original line segment. The golden ratio is computed when the ratio, so the reason why it's a ratio, because it's actually a ratio between two numbers. We start with the ratio of the longer segment A divided by, it's a ratio, so it's a quotient, divided by B. If this is to be the golden ratio, then this should be equal also to what? To the original line segment. That's why it's A plus B. Remember, A plus B is the original segment, the black segment here. So we are talking about the measures. So if we add that, that's the original segment. We divide it by the longer line segment, A. So if this is true, then the ratio that we get here is actually the value of phi. But what really is the value of phi? We will be arriving at that later. Now, we will continue this one. What is this? What are you seeing here? Actually, these are two equations, right? You can actually separate this one into two equations. Phi is equal to A over B, and phi is equal to A plus B all over A. Again, how did we arrive here? This is the definition of the golden ratio. It is a golden ratio if the ratio, this ratio here, is the same as this ratio. Because if it's not, then it's not the golden ratio. It's another ratio of numbers. So let us remember this one, these two equations here, because these two equations are our references, or are our information on how we compute the value of phi. Let's start with a new slide. So let us start with the first equation that we had a while back. Phi is equal to A plus B. Again, A plus B is the measure of the original line segment over the longer cut A. Arithmetically, we can separate this one. So we are dividing the quantity A plus B, the sum A plus B by A. So we can actually rewrite this as A divided by A plus, follow the operation, B divided by A. So we simply distributed our numerator with our divisor. What else can we do? Well, we have A over A. A number divided by its own or the same number is of course always 1. We are sure that A is not equal to 0 because it's a measure of some segment. So 1 plus B over A. How should we continue with this 1? Let us try to recall some information that we mentioned not very long time ago. It's like we mentioned this one a few seconds ago. Remember that the other equation that we arrived or that we have in the previous slide is this equation. Phi is also equal to A over B because phi is the golden ratio. Let us focus on this equation that we had the last slide. So we have phi equal to A over B. If we're going to get the reciprocal of each side, remember the concept of reciprocal. If you are given a fraction, so the fraction has a numerator in the denominator, the reciprocal is another fraction formed by interchanging the numerator in the denominator. So the reciprocal of A over B is B over A. How about phi? Well, the denominator of phi is understood to be 1, so its reciprocal should be 1 over phi. Now, why are we doing this one? That's because in our earlier expression, we have B over A. And what is B over A? That is our goal. We want to express B over A in terms of phi. So, B over A is the same as 1 over phi. Now, let us go back with this equation. So, phi is equal to 1 plus B over A, but B over A is the same as 1 over phi. So, we will simply change B over A with its equivalent. So, since they are just equal, we can change one by the other. Mathematically, why are we doing this one? We are trying to compute for phi, and our equation involves a lot of variables, actually, other two variables, A and B. And in mathematics, if we want to solve one equation, we need to get rid as much as possible of the other variables. Of course, when we get rid of the other variables, it has to be mathematically correct. We have now an equation involving one variable only. This means that we can now solve for the value of phi. But before we do that, we need to rewrite our equation first so that it would be easier for us to solve. Now, how do we do that? Okay, let us transfer all the terms here at the left side, or we call that putting the equation into its general form. An equation is in general form if the right side is 0. So 1 and 1 over theta from the right side, we're going to transfer it to the left side. Of course, by transfer, we mean the different properties of the operation addition and subtraction. So this equation becomes phi minus 1 over theta equals 0. That is the general form. The next step is to get rid of the fraction. I mean, to rewrite this fraction term here so that, again, it would be easier for us to solve for phi. It's real difficult to work with fraction. So how do we do that? We can multiply to the entire equation. Remember, if this is an equation, multiplying anything to each of the term will maintain the equality of the two sides. And if my goal is to get rid of this fraction and make it integral, then I would like to multiply it not by just any number but by phi. Because if I multiply phi to 1 over phi, the answer is actually 1. But if you do that, you need to do that to all terms. So let me do that. So first, we have phi times phi. We follow the operation 1. Next in line to be multiplied 1 and phi, negative 1 and phi. And then, the reason why we're doing this is to multiply 1 over phi by phi. Of course, 0 times phi is still 0. We multiply this one, the first term, phi times phi, it's like x times x equals x squared. Phi times phi is phi squared. 1 times any number is the same number, so 1 times phi is still phi, minus 1 over phi times phi is 1. So now we have a quadratic equation, and we need to recall again how we solve a quadratic equation. How do we do that? We can make use of, there are actually a lot of methods, but for this video, we will be using the quadratic, your very famous quadratic formula. What is your quadratic formula? If you are given a quadratic equation of the form ax squared plus bx plus c equals 0, then the root or the solution for the quadratic equation can be solved by using the quadratic formula negative b plus minus square root of b squared minus 4ac all over 2a. We go back with our quadratic equation that we get here, and apply the quadratic formula. So how do we do that? So what should be the value of our a? Since we do not see anything, that means the coefficient here is 1. B is negative 1 and C is again negative 1. And then we use these ones as input in the quadratic formula. So what do we get? Let me write again the quadratic formula, and then now we substitute. We are substituting. I hope you know how to do this. We simplify, so negative times negative 1 is positive 1 plus minus square root of, the square of negative 1 is 1 minus, well, that's minus, but you have a negative factor here, so that gives you a positive answer, plus 4 all over 2. 2 times 1 is 2. We simplify further, so we simplify the number inside the radicand. This is a radical expression. So we have 1 plus square root of 5 all over 2. We cannot further simplify this 1 so that it would remain exact. What we can do is to use our calculator and input this one so that we'll have an idea of the decimal approximation. The decimal approximation of this expression 1 plus square root of 5 all over 2 is actually 1.618. And what is this? This is the value of phi. This is the golden ratio. 1 plus square root of 5 all over 2 is the exact value of the golden ratio, and 1.618 is just an approximation. Just like your pi, you're saying that the value of pi is 3.1416, but 3.1416 is not the exact value, but simply an approximation of pi. So there you have it, the value of your golden ratio. Now, how are the Fibonacci sequence in the golden ratio related? Why are we discussing them in one presentation? Yes, you are right. They are actually related, and I will be presenting you how. You can see here already your Fibonacci sequence 1, 1, 2, 3 until 55. You can continue if you want. If you're going to take two consecutive Fibonacci number and then divide the latter by the former, then the quotient will actually approximate the value of the golden ratio. Let me show you that one. We start with 1 and 1, the first two numbers in the sequence, in the Fibonacci sequence. So if you divide the two preceding terms, well, of course, obviously, the answer is 1. We do that for 2 and 1. The answer, the quotient is 2. Divide that by the next one. Divide the next one, 3 and 2. 3 half is the same as 1.5. 5 and 3 is 1.667. So we repeat the process. Let's see what happens to the quotient. Alright, so let's observe what is really happening here. As we go on dividing a Fibonacci number by its preceding term, the quotient actually approaches the golden ratio. Remember, the value of the golden ratio that we computed a while back is 1.618. So that is the relationship of Fibonacci sequence and the golden ratio. The golden rectangle and the golden spiral. What is the golden rectangle? This is the definition. A golden rectangle comprises of squares that is represented by the numbers in the Fibonacci sequence. So you have a very small square here. That is a square. It's really small. I don't think we can see it. But this is a square. A side measures 1 unit. So that is the starting point of creating or constructing the golden rectangle. A square whose side measures 1 unit. Another one. And another square, a larger one. This time, the measure of a side of the square is 2. So we are following the Fibonacci sequence. That is how we construct the golden rectangle. Next is a square with side that measures 3 units, and then 5, and then 8, and then 13, and then 21, and then 34. And from these non-overlapping squares, we now create our golden spiral. Okay, that is your golden spiral. Golden ratio in nature. There's a lot of objects in nature that are associated with the golden ratio, the golden rectangle, and the golden spiral. Here is a Greek ancient architecture. It's called the Parthenon in Greece. Accordingly, if you measure the dimensions of that ancient architecture, it involves the number phi, or the golden ratio. The shells, this is a famous one. The spiraling of the seashells, its covering, is a golden spiral. Spiral galaxies are also an example. Typhoons, and even your face. How about that? Here is an interesting statement about golden ratios and your face, the dimensions of your face. The mouth and nose are each positioned at golden sections of the distance between the eyes and the bottom of the chin. Similar proportions can be seen from the side and then the eye and ear itself. On average, every person's body tends towards phi. It has also been said that more closely our proportions adhere to phi, the more attractive those traits are. Well, of course, it's up to you if you want to believe this one, but it's just saying that accordingly, if your face dimensions is nearer to the value of phi, then you are perceived as more attractive. In fact, I have made a little research on the most beautiful faces in Hollywood actors and actresses based on the value of the golden ratio. So I will only be presenting you the top 5. In the 5th spot are Kendall Jenner and David Beckham. It's 90.18 and 88.96% close to the number phi, or the golden ratio. fourth spot, you have Emily and Harry Styles. Your third spot is Kate Moss and Brad Pitt. The second spot is Kim and Bradley Cooper. And at the top spot are Amber Heard and George Clooney. 91.85% and 91.86%, close to the number fee respectively. Alright, that concludes our discussion on Fibonacci sequence and the golden ratio. I hope you learned something. I will see you in the next video.